Right. Am I muted or not? I think I'm not. Okay, perfect. All right, good morning, everyone. I guess we are going to start our third tutorial today. It's pretty easy tutorial. I think you will just enjoy it. It's not as hard as other tutorials that are coming, and also like the past tutorials were kind of like introduction, and you were not like very familiar with what with the course and what to do and so on. So hopefully this tutorial will be much better. Okay, so before we start, there are a few announcements. We decided that you guys are allowed to submit part B of the assignment as group submissions. So that means that you can work with your friends within your group and so on, and you can submit one assignment for all of you. Like for like if your group, like if you are like 5 students in one group, you guys can ask each other even after the tutorial and so on for part B, and you guys can submit only one assignment for all of you. That's okay. We noticed that sometimes people copy each other's assignments, and we are not actually like, it's the point of the assignment is you assess yourself. So it's a self-assessment. So we don't really want you to like copy it. Like we don't care if you copy it, but the idea is that we want you to understand how to solve it, even if it's hard for you at the first time. You can ask yourself, like you can ask other students, you can ask your friends, you can ask me as the TA, you can ask Professor Dr. Ayman as the course instructor and so on. So the idea is that we don't want you to just spend a lot of time just copying and so on and trying to disguise, like the assignment for like, so I cannot know that you copied it and so on. That's not the point. The point is that we need you to assess yourself to see if you really understand the concept that we are trying to deliver to you. And if everything is fine, that's perfect. We'll just give you like, we talked to Professor Ayman, Dr. Ayman, and he said he doesn't care. He won't give you like all the marks, but the idea is that we need to find a tool for you to use to self-assess yourself, and for us to understand also if you really understand the concept or not, because that would be like an indicator for us to move forward with the quizzes and for the final exam. So that's the first one. For the second one, I also noticed that you guys don't really show up. Like there are students who showed up for the office hours, but I think it's too early because like even like that's what happened. Like we have office hours on Wednesday, and then a couple of students show up and so on, but we stay for the entire time waiting for students to show up, but no one shows up after like these couple of students. But then right before the submission of the assignment, like on usually like Thursday night or Friday morning, I receive a lot of emails and a lot of questions and so on. So then what's the point of having like the office hours that early? Then we can move it a little bit to have the office hours right before the submission of the assignment. So I guess Friday morning would be good. So let's have a poll and you guys can vote on which time would be the best. Like if you prefer the office hours to be still on Wednesday from 3 to 4, that's completely fine with me. But I think also we need to know like if you guys prefer to have the tutorial or like the office hours in the morning or not. But from what I see from the voting, everyone is like going for like Friday 10. All right, that's good. That's cool. All right, I'll just give it 30 more seconds for everyone to vote. And again, like the idea of the office hours is to answer your questions and to spend time with you even like after the tutorial, so you can get familiar with any concept that you couldn't grasp like during the lecture time and during the tutorial. So because that's what happens normally. Sometimes you have a lot of like ideas and a lot of concepts and so on, but you're not really you didn't grasp everything, and that's completely fine. So you need some more help during the office hours to finalize everything with the course and so on. Okay, so I guess there are like 8 more people who didn't really vote. I hope these people are thinking about the vote, not just leaving, you know, like the Zoom session and doing something else and not really paying attention. So, okay, we need 4 more. Okay, probably like it's a good way to end it now, to be honest. I guess everyone is going for Friday 10 to 11. There's like more than 50%, and the other 50% are going 30% towards Friday from 1 to 2, and 20% going for Wednesday 3 to 4. Okay, so one more question. Is Friday 10 to 11, do you guys have other commitments during this time or not?
We have this lecture from 9:30 to 11:30.
Oh, okay. So again, what? Okay, so I guess I'll have to end this one and choose a different time. So it's literally from 10 to 11.
Our lecture for this is, yeah, basically.
So if I choose 11 to 12, that's better. You can do that.
Yeah.
Okay, because I
that
think
would
everyone's
usually
going
work.
for like this time, like early in the morning, not in the afternoon, because I understand, you know, if we spend like an hour like trying to work on the assignment, then you need, you know, a couple of hours to finalize the assignment and submit it afterwards. Okay, so let me edit the poll. Okay, so I guess we don't really need to edit that. So are you guys okay with going forward for 11 to 12? The majority, like not the majority, like the people who have a course or like a lecture from 10 to 11, so 11 to 12. Is that correct? That's okay for everyone?
Yeah.
Okay. Then we will have the office hours this week for Friday from 11 to 12. Okay, one more thing regarding the questions about the assignment. You guys can see that for each assignment, you have an email and a name for one of the 3 of us. It's either me or Sebastian or Munji. So you guys, it's preferred that you direct your questions towards the person who is responsible for the assignment, because that's how we, you know, like redistribute the workload between us as TAs, and we want you guys to help us like to do that. Like, so if I have the assignment today and I have my name on the assignment, so you guys are preferred to ask me, not for example to ask Sebastian or Munji, because they have other responsibilities this week, and I am responsible to answer you. And we rotate like these responsibilities and so on. So it's just kind of, you know, like how we do things, and we would like you to just collaborate with us. So usually like, you will have an email on the top of each assignment. So you just send your questions to this email. That's also after, you know, like you submit your questions already on the forum and ask your friends. Okay, so did everyone receive the assignment? Do you have the assignment already? Because we are going to work on like, you know, some of the concepts regarding the assignment. So if you have any problem with the assignment, you didn't receive it either on OWL or on Gradescope, just let me know now so I can fix that. If not, then I would just assume that everything is fine. And yeah, okay, so for part 1 or part A in this week or this assignment, we have 2 problems, 2 very straightforward problems. The first one is like kind of conceptual. We are using kind of, you know, like annotations for you to understand how to formulate the global stiffness matrix and the global load vector. And then afterwards, we will talk about like how to get the stresses within each element of the bar elements. And that we will do that for part A, the first question. The second question is kind of similar to the first question, but with different load settings and so on, and with different, you know, like constraints and boundary conditions. But instead of solving and explaining the second question, we will solve the second question on SAP 2000. So you can see how do I formulate the entire problem and so on. And then we can work on the groups to submit like the the tutorial, like the part A by the end of the tutorial. Okay, so part A, we have a bar element here. Actually, these are two bar elements, and these two bar elements are connected to two different springs from the end. We called the first element A, element 1, and the second element 2. And for each joint, we have like 3 joints here. The first joint here is B, the one in the middle is D, the one at the other end is C. And we gave you, you know, like the value of the spring constant equals 2EA over L. And we had two different, like we used the same setting or the same bar elements, and we used different load combination. For like figure A, we had only one point load at the joint in the middle, joint D. And for another different load settings, we had distributed load, P node, that is uniformly distributed within element A, element 1 and element 2. So one thing I would like you to know is that we have this, for example, in the tutorial, we have, you know, first case, like the figure A, and second case is like the distributed load and so on. In the exam and in the quizzes, you will not have this one because this is too easy, or you will not have like the other load combination only because it's also too easy, very straightforward. But you might have a combination of two, or you can have the combination of two and another third different load as well. So those are the basics. Again, I need to stress on that. Those are the basics, and understanding that very well will help you to be able to solve more complicated problems. All right. What do we want? We want you to evaluate the global stiffness matrix of the structure for each of them, and to evaluate the global vector acting on that set of structure. So if we're going to solve the first case or the second case, you know that the global stiffness matrix for the first one and the second one will be the same, because the global stiffness matrix is independent in comparison with the load that is acting on the structure. So in the course notes, you have for the bar element, you have the global stiffness, the local stiffness matrix. The stiffness matrix for each bar element is K 2 by 2 LE. LE is like the length of the element, and you have here like the matrix 1 minus 1 minus 1 1. This is the basic. And also you have the load vector, like the derivative for a linear axial load for the element or the acting on the element 1, 2. A joint 1, you have P1, a joint 2, you have P2. So the force vector is third P1 and 1/6 P2, and then 1/6 P2, it's the opposite, 1/6. So it's 1/3 of the load that is acting on the same joint, and 1/6 of the load that is acting on the other joint that is further away. And then you convert that again. So that's how you memorize it if you forgot. But anyways, you will just have access to that anyways. So this is the basic. So what if P1 equals P2? If P1 equal P2, that means that it's a uniform load, uniformly distributed load within the element, and that means that half, logically, without even looking at the equation, that means that half of the load will go to the first joint, and the second half will go to the other joint. If we put that on the equation, so if we you know, like assume that P1 equals P2 equals P, then 1/3 of P, we'll just put P1, we'll just put it P, 1/6 of P2, we'll put it P as well. Then it will be like 1/3, which is like 2/6, and then 1/6, which is like 3/6, which is 1/2, which is like P/2. And the same for the other joint as well. So that's the basic, that's what you start with, and then using that, you'll be able to solve the problems afterward. So let's focus on the first case that we have, in which we have only one concentrated load P in the joint that is in the middle. So for element 1, we have EA over LE 1 minus 1 minus 1 1 that we just took from the lecture notes. And we know that LE, or like just we noted that LE, like the length of the element is the entire length, because that's what is given in the problem. The entire length is L capital. So the length of 1 or the length of 2 is L over 2. So we will just remove LE and we will put L capital over 2, which is like 2EA over L. And that small detail, like you guys usually, like, I don't know, for some reason, you just use L, the entire L. So that makes that, like mess up the results and so on. So pay attention to the length, the entire length that is given, and the length of each element. Like for example, for the second problem, I purposely put each L separately. So you have L for the element 1 and L for the element 2. So that's very important to pay attention to these small details. And for like, that's the stiffness matrix for element 1. The stiffness matrix for element 2 will be exactly the same because they are identical elements. So it will be the same. So that's the local stiffness matrix, 2EA over L, 1 minus 1 minus 1, 1 as well. So without the effect of the springs, we are going to formulate the global stiffness matrix. So the global stiffness matrix is a stiffness matrix that has all the joints. How many joints we have here? We have B and D and C. That means that there are 3 joints in our problem, or in this problem. So for this row, this is B, this is D, this is C. And for the rows as well, this is B, this is C, this is D, this is C. So the same arrangement horizontally and the same arrangement vertically. And we know already from the past slide that for 1, which is like B, D, we have 1 minus 1 minus 1, 1. So we go forward. So 1 minus 1 minus 1, and only 1. So this 4 elements away from the other one, those corresponds to the first element, which is BD. And we go for the other element, which is DC. We will go, those 4 elements will be the 4 elements that that formulate the new global stiffness matrix that we have. So why do we have 1 plus 1 here in the row that has that corresponds to like D in the rows and D in the columns? Because we have 1 contributing, like we have like 1 or like 2 EA over L contributed from the first element and another 2 EA over L contributed from the second element. So that's why the global stiffness matrix for that 3 joint 2 bar elements look like that, only without the effect of the springs. So global stiffness matrix so far without the effect of the springs is 2EA over L, 1 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1. Before I go further, do you guys understand? Do you have any problems so far? If you have any problem or anything that is not clear, just let me know.
I was wondering, do we have to show the fact that we did it without the springs first, or like if I'm doing it, can I just do the
If you just know how to do it, just do it right away. I don't care. I need you just to get the right answer. But
okay.
It's easier at the beginning if you are not really familiar with how to put the like the factors and so on. You finish the global stiffness matrix first for the elements themselves without anything else, and then you add the effect of the springs. But if you can do it right away, do it right away.
Okay.
Any other questions, guys? Fantastic. Perfect. Okay. So that's the global stiffness matrix for the structure that we have so far without the effect of the springs. So what if we are going to add the effect of the springs? What will happen? So firstly, the first spring is attached only to joint B. The second one is attached only to joint C. So we will just add the effect, or like, you know, the stiffness constant, or like the spring constant, to the joint that corresponds to B from the column and B from the top, which is like this element. So this we will add here to EA over L, and for C also we will add here to EA over L. So that's how it will look. With adding the effect of the spring, we will have one more here because we were smart. We planned the problem ahead. So we had 2E over L, TA over L as a constant outside, because we saw that the constant here is 2E over L, and we knew that we are going to add already the spring stiffness or the spring constant to the global stiffness matrix. So we added here just one because it corresponds to EA over L, and one here because it corresponds to EA over L that is on the other end. We can do the same thing, but you know, sometimes we do it with numbers, so you have to be attentive to the numbers as well. So for example, if you formulate the global stiffness matrix after you formulated the local stiffness matrix and so on, and the constant here is like 500, and then I give you the spring constant is like 100. So you have to see these small details, so you know that, you know, you can just take or like, you know, the 100 equals, you know, like 500 equals like, you know, like 5 multiplied by 100 and so on. So you can just add 5 and you take the 100 outside and so on. So that's what I meant. But if you feel like you are going to be a little bit it will be tougher or something like that, you just multiply everything and then add the value to each element, or like to each like spot in the matrix and so on, and just finish it this way. But it's better to, you know, be attentive to that, because usually we have these kind of, you know, relations between the stiffness matrix that we have for the each element and the stiffness matrix or the spring constant. All right, so finally, our global stiffness matrix, after adding the effect of the springs and the one that actually corresponds to this problem, will be 2EA over L, 2 minus 1, 0, and minus 1, 2, minus 1, and 0, minus 1, 2. So this is the one that we are going to use to solve the problem in like, you know, to get like the displacement and to get the stresses and to get the strains and so on. So this is our final answer for the global stiffness matrix. Is everything clear? Do you have any questions regarding that? All good? All right. Let's move on to the global vector, the global load vector. Okay, so the global load vector is very straightforward in this occasion, because it's, again, we have only one vector which corresponds to the 3 different joints that we have, and the first joint is B, D, C. So we have 3, you know, elements, B, D, and C. And because we have only one load that is like concentrated on the middle joint, which is D, so we will add P here, and that's it. So our global load vector is 0, P, and 0, and that's it. And then if you would like to get the displacement, then we have like, you know, F equals K delta, and that's it. Just get your displacement right away. As easy as that. Any questions so far before we move into the second load case? That is fantastic. All right. The second load case is the same everything, same structure, but instead of having a constant load P acting on the joint in the middle, which is D, we will have a uniformly distributed load, which is P node. And For that case, we know that the global stiffness matrix will be the same, so we are not going to spend a lot of time redoing it again, because sometimes when you are like under a lot of stress in the exam and you have two problems and so on, but sometimes we make things easier for you so you can save time, but because you're under a lot of stress, you just say, okay, I have to, get the global stiffness matrix again and so on, but it's exactly the same. So also pay attention to that. So the global stiffness matrix is exactly the same. So we'll use the one that we already got from the last step. And the only thing that will be different is the global load vector. And for the global load vector, we can use either one, the logic. So for like the local load vector for like element 1, you know that it's uniformly distributed load, and the length is L/2, and we have P node here. So the summation of all the load acting on on element 1 is P node multiplied by L/2. So half of P node L/2 will go for, or will go to the first joint, and the other half will go to the second joint. So each joint will have P node L/4. That's the logic. If you feel like you cannot just do that, you can just go back to the equation, the generalized equation for like the linearly distributed load, which says that each load go, if you have P1 and P2, then the third goes to the close joint, and 1/3 of the load on the other joint goes to this one as well, and you will reach the same answer as well. But just pay attention to LE will be L/2 in this case. All right, so for each element, or for each element 1 and element 2, you will have P node L/4 for each element or for each joint. So when you are formulating, so this, okay, for element 1, this is for joint B, and this is for joint D. And for element 2, as you see here, the first one is for joint D and then for joint C. When you formulate the global load vector from these two local load vectors, you will have 3 elements, corresponds to B and D and C. So the first one would be P node L/4, and the second one would be the summation of these two loads, which is PLE/4 and PL/4 as well. So it's P node L/2, and then the third one corresponds to the load acting on joint C, which is P node L/4. Do you have any questions so far? Everything's clear? Any questions? All right. As I told you, guys, that will not come in the exam. The exam will be maybe, the summation of the two questions. So you will have like, distributed load like that, or maybe it will be, linearly distributed. So you'll have, P1 and P2 and so on, and you'll have load here, and you maybe have another load concentrated acting on, joint D as well, or joint B and C. So it will be like another step. It will not be like as straightforward as that, but we just wanted you to know the basics, and then you can just build up after that. All right, so that's the first problem. You will be asked to analyze that. And what if I asked you guys to calculate the stresses that is acting on element 1 and element 2? What will you do? If you go back to note, or like the course notes that Dr. Ayman posted already on OWL, you will see that there is a strain equation that is, written within, like the formulation of the stiffness matrix. But that strain is like du, which is like the derivative of the displacement, du over dx, which after like had the assumption of the shape function and so on. So it will equal minus u1 over L2. U1 is the displacement that you got at element at the first joint, and U2 is the displacement that you got at the second joint. So the strain, which is du over dx, is the it's like U2 minus U1 over LE. LE is like the length of the element. So you get the strain, you multiply that strain by the modulus of the Young modulus, and you get the stress. So a very common question that you guys usually have in the exam is when Dr. Ayman asks you, is this stress accurate or not? So how do you know? So usually you check the function of the stress. By checking that, you check the function of the strain as well. So when you see if the displacement is linear, that means that the strain is going to be constant because it's the derivative of the linear is constant. And when the stress is constant, you check if it's like a constant force and so on. So you know that if it's accurate or not. So how do you solve the question that usually asked by Dr. Ayman? When he asks about the stress, you look at the strain. And when you look at the strain, you're actually not looking at the strain, but you are looking at the displacement function, because the strain is the derivative of the displacement. So again, also pay attention to that, because you're going to use that in the course today, or like in the assignment, like the part A, and you're going to use it also in part B. Right, so that's all for the first question. Any questions so far before we move to the second problem? Just unmute yourself and ask the question if you have any question. No? Fantastic. Okay, so moving to the second problem, we are not going to solve this, or like we are not going to work on it like together and so on, but we will just explain it, and then I will go and work on it on SAP in front of you, so you guys can be familiar with the steps, and yeah, then you can solve it afterwards by numbers using hand calculations on your own, and then you can compare the results from SAP and your hand calculation. Okay, so we have a bar, and we needed to model this bar. So we asked you guys to solve this 2 times. The first one using 2 bar elements, and the second time using 3 bar elements. And we left it to you. We asked you to solve it, put the 3 elements the way you want. If you like to have here, this is 1 element, and you divide the second element, which has uniformly distributed load to 2 elements, it's your right to do that. If you'd like to do any other different arrangement, you have to justify that. So anyways, okay, so we will just jump into tab. So that's how the problem will look in SAP, and then that's how we get stresses as well from SAP. So I will just stop sharing this one, and I will jump into SAP. All right.
So just to confirm, when we're doing this, like you want us to be doing the calculations, not the SAP part of it. This is just for us to get used to SAP.
Exactly. I mean, like you can do the SAP part on your own, but you're not required to submit it as part of part A, but it's for you. Like, you know, it's for you to be familiar with SAP. And if you would like, you can just, you know, take screenshots of the submodel that you made, and then maybe you will get bonus if you had like any other problem with the hand calculation. And I know that you spent a lot of time, you know, like working on the submodel, and, you know, like just a small hand calculation error and so on, I will just give you a bonus. So the idea is that I would like to encourage you guys to work on SAP from early on, and then afterwards you will be familiar with that, especially for the second half of the tutorial after the reading week. All right, so let's jump into SAP. All right, so this is the problem, but I'm not going to work on it. So I will start from scratch. No. All right. So I did, oh, sorry. I need to start a new one. All right. So we would prefer to start with this one. You have to make sure that the units are in accordance with the units that in the course or like in the assignment. So I would prefer to start with N, like with Newton millimeters, because that will be like easier and straightforward. And we have two spans, and each span is 4 meters, which is like 4,000 millimeter. So we'll start with that. And I will just move this bar. And okay, so first thing, I will assign the joints. So the first one is free joint. So there's no any restraint in the joint in the middle. And end joints are fixed. So I will assign joint restrain, and I will put the fixed. So that is how the model look like. But before doing anything, we have to define a lot of things. So first, we're going to define the material that we have. So we will go for this, and we call it concrete. And we have here E equals 2, E 5, and again the bar is in the way, so that's the E for us, that's the concrete, that's the material, because this is very important, because in the calculation process it will use the modulus of elasticity from this information that I just added to the material properties. So that's very important not to forget to edit the material properties that you have. So this is the first. Yeah.
Can you go back to what you just did? You went a little fast.
Okay, so you just go to define material. So you press material, or like you will have like 2 preset materials. Usually one is for concrete, the other one is for steel. And even if you open it, like if you open the first one here, modify and show material, you will find it says material type, it's steel, right? And you go for the other one, modify, and you will see that material type is concrete. So you will go to concrete, and you will just edit the modulus of elasticity in the box that says like isotropic property data, and then you just put the value that is given in the course notes. So I give you in the course note, it's 10 it's 10 no, it's 2 multiplied by 10 over 5. You just put the value, and that's it. Very straightforward. Is that enough?
Yeah.
Perfect. Okay. We'll go forward. And then after you defined the, okay, actually, I would like to share with you the entire thing. So you guys will see what I'm doing. So that's, I'm sharing my screen. So we are here. That's the assignment. So that's the second problem that we are working on. So we just added this value. We added a modulus of elasticity. And now we need to define the element. So the most important part of defining the element is to define the cross-sectional area, because working on, or like using bar element, means that SAP will use 1. From the material properties, we'll use E, the modulus of elasticity. And from the frame, or like not the frame, like the bar assignment, it will use the cross-sectional area, which is A, and the length of the element, which is L. So at the beginning, we already added the L, which is like 4 meters each, but now we are going to add the cross-sectional area. So back to SAP. So we go again to define. And then instead of going for material, we go to sectional properties, the second one. And from sectional properties, we go for frame section. Again, here, there is a pre-assigned element, which is like usually is a steel element. So we go for add new property. Add new property, we press here. We had a different, like conversation box. We go for rectangular because it's very easy. And we will call it, like area 800 millimeter square. Okay. So it asks you like, what is the depth? So what's 800? 800 is like, 40 multiplied by 20. Let's go like that. So in order to make sure that everything is correct, there is a small box here. It says like section properties. So you open the section properties and you find all the properties are calculated already. So the most important thing for us when we calculate, you know, the cross-sectional or like the bar element, the cross-sectional area. So the cross-sectional area here is 800. So we are correct. And also if you are, you know, doing any other school work and so on, and you just need to get us a very fast way to get your moment of inertia about any axis and so on, use SAP. It's very efficient with that. So again, but make sure before moving forward that the material is concrete, because it's pre-assigned already to be steel. So we get it to be concrete. So we have the concrete, the one that we just assigned. So in the calculation process, it will take the modulus of elasticity that we added to the material property. And then the area, or like the value of the area, will be taken from the assignment that we added for the element. So that will be the assignment that we have here. Then okay, so our element is area 800 millimeter. So in order to assign, okay, let's get back. Sorry, my laptop is pretty slow. Okay, so just highlight everything and assign frame section. All right, so we go to assign frame sections, and then we choose our section that we just defined and apply OK. And then you will see that the section name, or like the section assignment, became area 800 millimeters that we just defined together. All right, so now we have the material assignment. Now we have the assignment of the restraint for each joint, and also we have the assignment for the properties for each element. We only need to add our loads. So in order to add our loads, we need to define a new load pattern, because it's not added. We will have only the dead load. So we need to add another one. We'll call it question 2, because this is question 2. And we will use that type would be life load, because we don't want any self-weight multiplier. It will be only the loads that we were going to add without any self-load added, and add new load pattern. That's it. And then we will highlight the joint that we have here in the middle, because if we go back to the question, we will find that we have concentrated load added to the mid joint. And we are, you know, solving the first problem as in use 2 bar elements first. So for the 2 bar elements, we will have one here and the joint that is in between the 2 bar elements. So we'll have here 10 kilonewton, 10 kilonewton force in the middle. So go back to tab. And what if I just set assign joint load force, and you know, I choose the load pattern would be question 2, and I said okay in the global direction, and I said okay it will be 10. Is that correct? Because it's written here it's 10 kilonewton. What if I just go here and I just say 10? Is it correct?
No, it's newtons, not kilonewtons.
Exactly. So many times this question or this error, so many students fall in this error. So it is 10 kilonewton, not 10 newtons. So it's 10, and then you multiply by 3, 10 over 3. So that's the first load that you have here. So this is the first concentrated load that corresponds to the load that you are adding, which is like 10 kilonewton. And then we need to add 10 kilonewton per meter, which corresponds to 10 newton per millimeter. So we will go and we will highlight the element here, and then we will assign frame load, distributed load. Okay, guys, assign frame load, distributed load. And then we go, we say, okay, the load pattern is question 2 in the global system, and we need to be in the X direction, and it's going to be force, and it will be 10 newton over millimeter. and that is the correct one, because Newton over millimeter equals kilonewton over meter. So it will be 10. So we'll apply that, press OK, and then we can see that it's 10 and it's distributed. How do we know that it's distributed? By seeing that there are a lot of arrows throughout the entire length. So that's it, as simple as that. And then you just press this play button, which means the run, and you say, okay, I don't really need the dead load case and the model case. So we just do not run those. You would run only question 2. And then we go for run now. And we will call this tutorial, right? And here we go. That is the stress. So we go for the deformed shape. Question 2. Okay. And that is C. So that was the location of the joint before running the model. And then after running the model, you can see that it's completely understandable that it's moved from the 0, 0, 0 to another location. So you go right click on that. You can see that it moved translationally, and that is the delta that it moved. And the delta is in millimeters. You can see that from the units here. So so here you go. And then if you'd like to check the stresses will be like more detailed. So you go for frame, stress S11 contour, and that's it. So you'll find it's pretty constant is in this side, because you don't have any forces here. But the reality, okay, so SAP give you the reality of that the stress, because we are using actually frame element, but we are using it only in one direction. So it's giving you more detailed answer. But the answer here will be corresponds to the answer that you should find from the hand calculation solve, like the hand calculation results. So that's it for this tutorial. Now we will open the breakout rooms so you guys can work on that together. And if you have any questions, I will be around, me and Sebastian and Munji as well. So yeah, feel free to join the rooms, and yeah, we'll see you.